try to give you an overview of electrical in about 5 hours. So we're going to take 12,000 hours and give it into 5. So that's how it works. And we're happy you're here. That's Mrs. Laraway, my lovely assistant in the back. She's going to be doing all of this. The purpose of the class is to give you a basic knowledge of electricity. We're not going to try to teach you to wire houses or machines or anything. It's just an overview. And we want you to, we're going to do a lot of safety. We want you to know what not to do when you're going to do something, and things to stay away from as best we can. Now you've got handouts, notes, and they're based on the presentations that we're going to do. And if you have any questions, just raise your hand, let us know, and we'll do our best to answer them. And pay attention. There's going to be a test, Matthew. Yeah, there's going to be a test. Yeah.
2 tests.
Okay.
2 tests today. Yeah.
Oh, 2 tests today.
Yeah.
Now, this class is designed to get you to pass the test.
So don't worry.
No worries. No worries.
So tell them a little bit about why you became an electrician.
When I was young, my next door neighbor, we were poor. The next door neighbor was an electrician, and he seemed to have everything. Happy family, happy. So as a child, I decided I wanted to be an electrician because I saw what they had and I wanted it. It wasn't only until after years later I found out that they were Christians that it made a difference. So, and through them, I got saved, and Mrs. Laraway got saved. So, but it was.
Because God worked it out that he could have an apprenticeship with this.
Oh yeah, I ended up getting an apprenticeship, and yeah, God is good. God he can really work things out. So that's pretty much my testimony in a little nutshell. So, but it all worked out. God is good. So I think we have a video.
We do.
Our lovely assistant will get that up.
Hey there guys, Paul here from theengineeringmindset.com. In this video, we are going to be looking at how electricity works. Now this is pretty essential knowledge for any engineer, so we'll run through the basic parts of what you need to know. So let's start at the very basics, and for that we need to take a look at the atom. Everything, including you, is made from atoms. All the materials we use are made from atoms. The materials are just different because the construction of their atoms are slightly different. The atoms are made from 3 particles, 2 of which are found inside the nucleus, and the 3rd particle sits outside this. At the center of the atom we have the nucleus. Inside the nucleus we have the neutrons, which have no charge, and we also have the protons, which are positively charged. The neutrons and the protons are much heavier than the electrons, so these will stay within the nucleus. Surrounding the nucleus are different layers of orbital shells. These are like flight paths for the electrons. The electrons flow along these flight paths, much like a satellite orbits our planet, except that the electrons travel at almost the speed of light. The electrons are negatively charged, and they are attracted to the positive charge of the protons. The electrons orbit around the nucleus in these orbital shells, and there are a set number of how many electrons can be in any one orbital shell. The number of protons, neutrons, and electrons an atom has tells us which material it is. Atoms hold on to their electrons very tightly, but some materials will hold on to them more tightly than others. The outermost shell is known as the valence shell, and in this shell some materials have loosely bound electrons which can flow to other atoms. Atoms which can pass electrons are called conductors, and most metals are conductors. On the other hand, atoms which do not have free electrons, and so they can't pass electrons between other atoms, are known as insulators, and these are things like glass and rubber. Now we can combine these materials to safely use electricity by having the conductor in the center, which allows the electrons to move, but surround this with an insulator to restrict where they can flow to, i.e. not into us, which keeps us safe. If we look inside a slice of copper cable at the free electrons surrounding the nucleus of the copper atom, you'll see that the free electrons are able to move to other atoms, but this happens randomly in any direction. If we then connect the slice of copper cable to a closed circuit with a power source, such as a battery, then the voltage will force the electrons to move, and this will then all flow in the same direction to try and get back to the other terminal of the battery. When I say circuit, this just means the route which electrons can flow along between the two terminals, the positive and the negative, of a power source. So we can add things into their path like light bulbs, and this means that the electrons will have to pass through this in order to get to the other terminal. And so we can use this to create things such as light. The circuit can either be open or closed. In a closed circuit, that means the electrons can flow around, and in an open circuit, this means that the electrons are not able to flow.
All right.
You need a volunteer.
I need a volunteer. We're going to do a magnet demonstration.
Good job.
That's a good volunteer right there. Now, this is a representation of what goes on with magnets. I'm going to try to keep them so they don't go together. See how they, okay, now turn yours around. See how they
Have them
feel
turn
the
so they can
force?
see it. Chuck. Have them turn around so they can see it.
Oh, turn around, yeah. Okay, well, it just wants to push it all over because magnets are cool. All right, thank you.
So we're pretending in that demonstration that those are electrons. An electron, as we just saw in the video, is negatively charged. The electricity is a universal force. So in the electrical force, opposites attract, like charges repel. Because all electrons are negative, they repel each other. But like we just saw with what they were doing there, when they're just when they don't have any force behind them, they just go off in random, directions and everything.
So what
So-
we have here is, this represents a conductor. These are the electrons. And as they push down, some of them are losing their strength. See? Try it. Cool, huh?
But the electrons cannot flow until there's what, Mr. Laraway?
Electrons need to flow in a conductor.
But they have to have a force or a pressure.
So the force or pressure to move them is voltage.
Yeah, it's voltage.
We're going to see another video on that.
So that's why you can grab a copper piece of pipe there as a conductor, but it's not going to hurt you because there's no voltage in there. You apply electricity to it, a power source, then yeah, you'll have problems.
Alrighty.
I think you got trivia.
Trivia. Okay, what part of the atom produces electricity?
Raise your hand if you know the answer.
Raise a hand if you got an answer. Matthew. Okay. Guess again. Okay.
There's a couple.
Okay, we had a hand up here.
Yeah.
No.
What's our question?
Okay, what part of the atom produces electricity?
Okay.
The elect.
Good job.
Good job.
They sound the same.
Okay, who can name a material that's a good conductor? Copper's good, yeah. Copper, metal, good job. All right, who can name the material that's a good insulator? Rubber, good job. All right, what is the term for electrical pressure? You know, to get this stuff to move down the line, what do we need to have that happen?
Charge.
No. No. Okay, something has to push this.
I know.
Electrical pressure. Okay, Mrs. Laraway, what do you know?
You need voltage.
Voltage.
Voltage is electrical pressure or force, and that's required to make things do it. Do I get a candy bar?
You do.
Okay. All right. Now we have another video.
We're going to find out how the power gets from the power station to you.
Remember, electricity is dangerous and can be fatal. You should be qualified and competent to carry out any electrical work. So electricity is generated at the power station, which is usually located far away. The power station generates AC alternating current and is connected to a step-up transformer. This transformer increases the voltage to reduce losses and is connected to the grid. The grid carries high voltage electricity over long distances over to the towns and cities. Once it reaches the towns and cities, it will enter a step-down transformer, which will decrease the voltage to a safer level. From here, it will be distributed locally into smaller circuits on different streets or groups of properties. Connected to these distribution cables will be smaller transformers, usually pole-mounted, which again reduce the voltage down even further to a level safe enough for residential use. On the property will be an electricity meter, which will quantify how much electricity has been used, and the electricity company will use this to invoice the property. The transformer will be connected to the electricity meter by some cables which will either run above ground or underground. These cables will be two hot wires and a neutral wire. Inside the transformer we have two coils of wire. The primary coil is connected to the power station and the second coil will be connected to the property. The two hot wires are connected to each end of the secondary coil and the neutral is connected to the center of the coil. Now don't worry about that too much for now. We're going to look at this again later in the video to understand it. So if we zoom into the property, we find a main service panel, which is sometimes called a load center or breaker box. If we remove the cover and look inside, we first find the main breaker. This is usually at the top of the panel, but it might be at the bottom. The two hot wires from the electricity meter will connect directly to the lugs on the main breaker. Coming out of the main breaker will be two main bus bars. These are basically exposed metal sheets which carry electricity to the circuit breakers. Notice I've shown the current flowing backwards and forwards. That's because this is AC or alternating current. These bus bars as well as the lugs are not insulated, they are live or hot. The main breaker can be manually flipped to cut the power to everything downstream of the main breaker. The main breaker will also provide overcurrent protection to the property. It is rated to handle a certain amount of electrical current passing through it, typically between 100 and 200 amps. If this value is exceeded, then it will trip automatically to try and protect the property and its electrical circuits. Inside the panel, we also have a neutral and ground bus bar. This is basically a strip of metal with lots of holes and screws in it. The neutral and ground wires will sit in the holes and the screws will lock them in place. In this example, we have a block on either side of the panel. As this is the main panel, the two bus bars can be joined together. So we have a connector bar between them. That way we have a shared neutral ground bus bar. Sub-panels must have their bars separated, but that's a topic for a separate video. From the electricity meter, we'll have the neutral wire connected to the lug on the top of the neutral ground bar. Notice the green screw. This is bonding the neutral bar to the metal casing of the service panel. The purpose of the neutral bar is to return the used electricity back to the transformer. It does actually get a little bit more advanced than that, but we're going to look at that in a more advanced, complex video. This is just covering the basics. So the two hot wires will provide electricity, and once it is used, it will return to the transformer via the neutral bar. It is still AC alternating current, but to make it easier to visualize, I've only animated the current flowing in one direction, so you can see the path. Now coming back to the panel, connected to the bus bar, we'll have our circuit breakers. These will look something like this with this black plastic casing and a toggle switch on top. The circuit breaker controls the flow of electricity into individual circuits in the property. It can be manually tripped to cut the power, but it also has two important features. The first feature is overload protection. The circuit breaker is rated to handle a set amount of electrical current. When appliances or lights are connected to the circuit, they will each increase the current in the circuit. If too many things are plugged in and turned on, then eventually the current will be more than the breaker can handle, and the breaker will automatically trip to cut the power off to the circuit and protect the property. The second feature is short circuit protection. When the hot and neutral come into direct contact with each other, the current will dramatically increase, almost instantly. When this occurs, it creates a magnetic field which will trip the breaker and cut the power automatically. Let's have a look at how the circuit breaker is connected to the electrical circuit. In this example, we will connect to a simple light fitting which is controlled by a switch. We take the hot wire from the circuit breaker and run this to the switch. We then run another wire from the switch and over to the light fitting. From the light fitting, we have a neutral wire which carries the return current back to the neutral bus bar. We take the ground wire from the metal casing of the ceiling box and the switch, and we also join this to the neutral bus bar, as in this case it's shared. The purpose of the hot wire is to carry the electrical current over to the light fitting. The purpose of the neutral wire is to carry the used electrical current back to the main panel and then back to the transformer. The purpose of the ground wire is to provide protection for a fault current. If, for example, the hot wire came loose and touched the metal casing of the light fitting, the ground wire provides a low resistance path back to the panel. Without this path, electricity could flow through you if you touch the metal box. As the current flows through the ground wire, it will increase the current and that will trip the breaker automatically. So the electricity flows through the hot wire, through the main breaker, down the main bus bar, and into the circuit breaker. From there, it flows along the hot wire, across the switch and light, then back along the neutral wire and into the neutral bus bar, along the neutral bus bar wire, and back to the transformer. I've animated this using AC alternating current, but to make it easier to understand the path, I've shown it flowing in a single direction.
All right, we just happen to have a panel. This is not the one that I had up there because I don't have one that big. So here's the cover. Okay, this is a breaker box. This is a small breaker box, and I don't have a big one. But you can see inside the ground bar, the ground bonding screw, a circuit breaker, the main lugs. This panel would be, if you wanted it in your barn, needed a few circuits, you would put this out there. And it's all rather simple. Right? Okay.
So how is this different than the main breaker?
This is different from a main breaker panel because this is a sub-fit panel. Main breaker panel would have the main lugs. Remember, they had the two big lugs. They had a main breaker up here, and then they had bus bars. This does not. And it has these are called knockouts. You knock those out, you have to have a connector for whatever wire you have for the appropriate size. So, miss anything, Miss Laraway?
Well, inside the cover there that they're passing around.
Oh, yeah, look inside.
We did put a picture of a main panel just so you can see the difference. Last time we did the class, we did have a main panel, but it got installed in somebody's garage.
In somebody's garage.
So, this is a sub panel, and but there is no main breaker. That's kind of the main feature there. That if you needed to turn off all the power, you'd have to go to your main.
The main breaker will turn off the entire panel. This you have to turn off every breaker. All right, Miss Laraway, what's next?
I think you have some trivia.
Oh, trivia. Well, what kind of electricity comes from the power plant? We talked about two different kinds.
Alternate current.
Alternating current, very good.
All right.
Good job. What's another name for the electrical panel? Breaker box, load center.
Is that Dayton?
Okay, what color is the bonding screw in the panel?
Green.
Green. We got a bunch of correct answers over here. How much voltage is provided by a single pole breaker?
220.
120. Real close. And everything that you do in houses is 120. You get 220 for either dryer or range. That's 220.
As we saw in the video, the power coming from the power company is 240 volts.
Yeah.
But when it gets to your panel, it's split in half. And so you're only using one side of that.
Yeah, you would normally have a main breaker. The feed lines would go into the main breaker. They would feed each bus bar. And each bus bar, where this plugs in, is 110. Now, there are 220 breakers. We'll show you all that stuff in a little while.
And one important feature always is you have circuit identification labels. This particular one has it on the front. Because in a main panel, you have an extra cover. Take this cover off because that's where all the killer electricity is inside. But these particular sub-panels don't have that extra hinge cover on it. They just have this cover here. So on a main panel, inside that first cover, you have your labels. But it's very important always to label correctly.
And
your
just because
circuits.
they're labeled, doesn't mean that's what it is.
So if you like buy a house or working on a house and you want to turn off the circuit breaker and you just open it up, you can't trust what's written in the main panel because they might have written it down, they might have changed things.
Well-
Sometimes they don't write anything down, so.
Sometimes they'll add a circuit and the wire is not long enough. So they'll rearrange the breakers so the wires are long enough and then they forget to change the
To
label.
write down what they did.
Yeah. So you have to verify. You have to verify everything. Sometimes a couple times because I've been shocked because when I worked at Ford's, we'd work in pairs. Well, my partner went off to turn off the circuit we were working on and it was labeled. So he said, okay. And we were removing a box like this and my side cutters, which I'll show you later, shorted out 480 volts, and the copper from that welded just burnt big holes in my glasses. So don't trust the person you're working with, and don't trust yourself. Verify. Just verify. What's next, Mrs. Laraway?
Well, as you saw on the panel, he kind of mentioned that when that power comes in from the power company into your power panel and you start using electricity, guess what?
They said the word meter.
Yes, and it's, yeah, he said the word meter. And what is the meter?
The meters.
How the power company charges you for what they
That's right.
give you or what you use, which is why your parents may be always saying, turn the lights off, because
A lot better now with LEDs.
it costs money. So we have a video on explaining that and kilowatt hours, because that's how you're going to get billed.
Welcome to the Enphase Homeowner video series. If you've ever taken a glancing look at your electricity bill, you know you are being billed for kilowatt hours. But what does that mean exactly? In this video, we tackle that question. A watt is a common unit of measure for electrical power. So if a watt is a measure of electrical power, what exactly is power? Power is a measure of the instantaneous electricity being used when you turn on any electrical appliance. You see power requirements called out in watts on labeling for everything, from light bulbs to microwaves. Kilo means 1,000, so a kilowatt is 1,000 watts. However, both watts and kilowatts are only a snapshot of instantaneous electrical usage. Energy, which is what we really care about and what the utility company charges you for, is that accumulated amount of power being used over some period of time. Energy is expressed in kilowatt hours. Here's an analogy that might help simplify the concept. Imagine you're driving a car. Your speed or rate of travel when you look at the speedometer is the equivalent of power or rate of energy consumption. But you know that looking at the speedometer doesn't tell you anything about how far you've gone. For that, you need to look at your speed over the time you've been driving. Energy is the equivalent of distance in this analogy. To understand how much energy you've used, you need to know how long you've been consuming a specific amount of power. Energy is power over some period of time. In small amounts, we measure energy in watt hours. Energy sized for a household, we measure in thousands of watt hours or kilowatt hours. Let's illustrate this with a couple of examples. A kilowatt hour is 1,000 watts used over 1 hour. If you burned 10 100-watt bulbs for 1 hour, you would use 1 kilowatt hour of energy. Or if you forgot to turn off a single 100-watt bulb for 10 hours, you would also burn a kilowatt hour of electricity. Taking that last example a step further, if you left that bulb on every day while at work or school, you would burn 260 kilowatt hours per year. At 25 cents per kilowatt hour, that single bulb left burning each workday would cost you $65 per year. You definitely want to turn off all the lights before leaving the house and switch to low wattage LED bulbs. Now you know. Kilowatt hours are a measure of energy, which is power over time. Your utility bills you for the energy or the electricity you consume in kilowatt hours.
Okay. That's all they had to say. All right. So, we have another video. Because once the power gets into your power panel, we need to know what's it do, where does it go, how does it get there. So, because it doesn't do any good if it just sits in your power panel. You want to be able to use it. So, we have a video that explains hot, neutral, and ground wires.
Gonna click on it again.
He's not talking to us.
It's a good thing we had the
It's up by
scientists.
that
Oh, I'm sorry. What happened?
Qualified.
Need you to remember. Number one, electricity will only...
That's why Pastor Steve is here. He's the technical.
Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be looking at the difference between the hot, neutral and ground wires, as well as the function of each with some worked examples. This video is for homes in North America. If you're outside this region, then you can still follow along, but your system will work and look a bit different, so do check out our other videos. Remember, electricity is dangerous and can be fatal. You should be qualified and competent to carry out any electrical work. Before we get into this video, there are 3 things I need you to remember. Number 1, electricity will only flow in a complete circuit. If you come into contact with an electrical conductor, your body might complete the circuit. Number 2 is that electricity always tries to return to its source. And number 3, electricity will take all available paths to complete a circuit, but it will take preference to a path with less resistance, and so more current is going to flow in that path. Okay, so we're going to be looking at the hot, neutral, ground wires for a typical North American residential electrical circuit. First, we'll see a really simple circuit to understand how it works, and we're going to apply this knowledge to a complex residential installation. When we look at a simple electrical circuit with just a battery and a lamp, we know that to turn the lamp on, we need to connect both ends of the wires to the terminals of the battery. Once we connect these wires, the circuit is now complete and electrons can flow from the negative through the lamp and then back to the positive terminal. So for the circuit to be complete, we need a wire to carry the electrons from the power supply and over to the light. This wire is our hot wire. Then we need to connect another wire from the lamp and back to the battery for the electrons to get back to their power supply or from their source. Now this wire is our neutral wire. The hot wire carries electricity from the power supply and it will take this over to the load. The neutral wire carries the used electricity back to the power supply. If we look at a residential electrical system in North America, then we will find 2 hot wires, a neutral wire and some ground wires. If you want to see in detail how this all works, then check out our video for that, links in the video description below. Now imagine for a second that the home's electrical system is connected to a battery and we have just 1 hot wire and a neutral wire. As we saw with a simple circuit, for the light to turn on, we need a hot wire to supply the current to the load, and we need a neutral wire to return the current to the source. Electricity therefore flows through the hot, through the bus bar and the circuit breaker, and into the light. It then travels back through the neutral and over to its electrical source. Now, of course, homes are not connected to batteries, they are connected to transformers. So we're going to replace the battery with a transformer, and there we go, we have a complete circuit. The electricity in this circuit is AC alternating current, which is different from the DC direct current which we saw with the battery. With DC, the electrons flow directly from A to B in only one direction, much like the flow of water down a river. But in our homes, we have AC alternating current, which means the electrons alternate their direction between forwards and backwards, much like the tide of the sea. Now in North America, we have a split phase supply to most residential properties. So we have the 2 hot wires and 1 neutral wire. We simply have 2 120 volt coils which are connected together in the transformer. The neutral is then connected to the center between the 2 coils. When we connect our multimeter between the hot and the neutral, then we're going to get a reading of around 120 volts. And we get the same reading for the other one. That's because we're only using half of the coil in the transformer. But then when we connect between the 2 hots, we get 240 volts because we're using the full length of the transformer. Don't worry about it too much for now, we're going to cover that in a more advanced video. Okay, so the hot wires carry the electrical current from the supply and over to the load, and the neutral wires carry the electrical current from the load and back to the supply. So what does the ground wire do? The ground wire, under normal operating conditions, will not carry any electrical current. This wire will only carry electrical current in the event of a ground fault. Hopefully, this wire will otherwise never ever be used at all in its entire life. It's just there for an emergency path for the electricity to get back to the power source instead of it passing through you. The ground wire in most cases is a bare copper wire. It's uninsulated, but in some cases it is covered with a green insulation. This wire has a very, very low resistance, so electricity will prefer to travel along it because it's easier and can get back quicker. Now if we go back to the simple circuit with a battery and a lamp, if we now run another wire, we run this from the positive terminal over to the lamp, and we connect this to the metal of the lamp holder, and this is effectively our ground wire. As you can see, it's not being used to carry electricity. If the hot wire touches the metal casing, then the electricity will now flow through the ground wire instead. If the hot wire is connected to both the neutral and the ground, then it will now flow through both wires back to the source. But as the ground wire has less resistance, then more current will flow through it. When electricity finds a way to leave its circuit and return to the source through a different way than its neutral wire, this is called a ground fault. Coming back to the house, the electricity flows through the hot wire and into the light and then back through the neutral. But if the hot touches the metal casing, then it will instead flow through the ground wire, back to the panel, through the bus bar, and then back to the transformer via the neutral wire. The ground wire has a very low resistance, so it causes a huge and instantaneous increase in current, which will trip the breaker. We therefore connect the ground wires to anything that could potentially become a potential path for electricity to leave its circuit, such as the metal pipes, the metal plates and the light switches and the outlets of their boxes. We also need to run one to the outlets because often our appliances are made of metal or they're covered with a metal casing, things like washing machines and microwaves. When you look at a receptacle and plug, you'll see that there is a hot terminal, a neutral terminal and a ground terminal. The casing of something like a washing machine is connected to a ground wire in the lead, which goes to the plug, through the receptacle, and back to the panel to save you from an electric shock. Now, let's say you're outside with no shoes on and the ground or the soil is moist. If you touch a hot wire, you could complete the circuit and the current may pass through you to get back to the supply. In this case, the resistance is going to be very high, so the current might not be high enough to automatically flip the breaker and cut the power. This will likely lead to the person's death. Luckily, we have the GFCI receptacle or the GFCI breaker. GFCI stands for Ground Fault Circuit Interrupter. We're going to look at a circuit breaker version, but essentially they're going to work the same. This GFCI breaker is going to be connected to both the hot and the neutral of the circuit, so we can monitor the wires and ensure that the current running in the hot wire of the circuit is equal to the current running in the neutral wire of the circuit. If the current is not equal in these two wires, then it is clearly flowing back to the source via another route. We then have a ground fault. The breaker will realize this and very quickly and automatically flip to cut the power and kill the circuit. Connected to the main panel, we will find a thick copper wire which leads out to a ground rod. The ground rod is buried into the ground outside near the property. This rod is not used for ground faults. Its purpose is to dissipate static electricity and external high voltages like lightning strikes. There is also a ground rod connected to the neutral at the transformer. Many people think that during a ground fault, electricity flows through the ground rod and into the earth. But remember, electricity tries to get back to its source. It doesn't just go into the earth. And as there is a ground rod at the transformer, then there is a potential path for the electricity to get back to the source. But this path will have a very high resistance or impedance. And as we know, electricity will take preference over the path with the least resistance. So as we already have a very low resistance ground wire, which provides a path directly back to the source, the ground fault is going to take this route instead. When it comes to lightning, the source of lightning is essentially the earth. So lightning is always trying to get back to its source, which is the earth. If lightning strikes the utility cables, it will flow along the wires to get to the ground rods of both the transformer and also your main panel. It's going to do this to try and get back into the earth. If it wasn't for this, then it's going to blow all our circuits and it's going to cause house fires. Now,
alright, that's one of my favorite videos. What kind of electricity does a battery provide?
Raise your hand.
Direct current. Okay. Where does the electricity always want to go? Everybody. Back to its source. Alright, what electrical device protects you in wet areas?
Ground wire.
No, it's a device. Type of breaker.
Oh, super.
Type of
GFCI.
GFCI, ground fault circuit interrupter. Either a breaker or a plug. Most of your kitchens will have the ground fault. Your bathroom will have a ground fault. Alright, what protects your house from lightning strikes?
Yeah.
Come on, Matthew. Ground rod. Good going, Matthew. Alright, we're going to have electrical safety PowerPoint. And my lovely assistant gets back here and starts it up.
Well, you probably noticed already from the videos, they all start out with electricity will kill you, can kill you. So, and I always like to say, no offense to plumbers, but if you're a plumber and you make a mistake, you might get wet. If you're an electrician and you make a mistake, you might be dead. So, the most important thing we can teach you, I think, in this class is some safety, because electricity is very dangerous. And you think, well, I'm not ever going to be an electrician, doesn't matter. We are using electricity all the
When you
time.
become a homeowner, then you start fixing things.
I mean, because we live with electricity. It's every house, every building you're in. Outdoors, there's electricity, and there's some areas that maybe you don't think about that you're affected by electricity. So I'm going to show just a slideshow. I'm going to narrate from the back, so you'll just hear the voice from behind. If you can't hear me, I'll talk loud. Raise your hand if you can't hear. But like I said, we want you to be safe. And so we have our basic electrical safety. Every year 1,000 people die and 30,000 people suffer from injuries from electrical mishaps. Now this is actually kind of an older statistic, so it might be higher now. But we don't want you to be one of these statistics, so that's why we're showing you this. Let's see if I can get this to move now.
So remember, you got to click the three dots and go to full screen.
So, and our disclaimer for this, like Mr. Laraway said earlier, is, present. Okay, that's why I had to do that. Okay, thank you. That this course is not going to license you to work on electrical equipment or qualify you to work on electrical equipment. It's just for your, informational purposes. Whoops, I went too fast. So, and the objective of this whole class, but particularly this section of the class, is to make you familiar with the fundamental concepts of electricity, to make you familiar with the effects of electricity on the human body, so you can recognize common electrical hazards and be familiar with the protective devices, which some of all has already been covered in some of these videos. This is a basic unit review. You have voltage, which is measured in, guess what, volts, and it is electrical pressure or force. It's not the same as power. Power is watts. Voltage is electrical pressure or force. That's what forces those electrons down the line like we saw in the magnet display. You have current, which is measured in amps or amperes. It's electrical flow, which is how many electrons are passing a set point per second. It can be measured, and it's measured in amps. And resistance is measured in what's called ohms, which is the restriction of electrical flow. So if you see that little cartoon up there, the little guy's trying to squeeze down the wire. He's an electron, but it's trying to measure him in amps, and the volt guy is trying to push him through, but the ohm guy is up there trying to resist his flow. So that's just a little cartoon representative of actually a mathematical formula called Ohm's law. It was developed by a German scientist way back in 1820. His name was Georg Ohm, and so that's named after him. Volts was actually named after an Italian scientist named Alessandro Volta. So, and amps are actually named after a French scientist whose last name was Ampere. So, all these, you wonder where all these names came from. They are named after the scientists who discovered these concepts for electricity. So, have you ever been shocked? Raise your hand. Who's ever been shocked? And we all have. So here's some basics as to why that happens. Electrical shock happens when the contact of, and it says human body here because this class is for humans, it's not for dogs or cats, but they get shocked too. In fact, we used to have a dog who liked to play with a battery, and every time he touched his tongue, he would get a shock. But he thought that was so much fun, he kept doing it. But anyway. So, anytime your body comes in contact with a source of electricity that causes sufficient current through your skin, muscle, or hair can give you an electrical shock. And why is this? Because your body is a good conductor. The human body is 72% water. And when electricity enters your body, it flows through your blood vessels because your blood, which is liquid, is a good conductor. Now, you have dead skin cells all over your body all the time, and they can resist or slow down the electrical flow to a point. But that resistance will decrease if your skin is wet, like if you've been swimming or in the bathtub or sweating, or even if the humidity is high outside, or with increased voltage. Because when you get up to 450 to 600 volts, that will actually break through your skin and enter your body. No matter how much dead skin you have on the outside, that much voltage is going to get into you. Other factors that affect the resistance or the slowdown is the point of contact between the body and the current. In other words, where does the current enter your body and where does it exit? And how long the contact is, the shorter, obviously, the better. You know, if you get shocked by a doorknob, how you jerk away right away, that's a short contact. That's good.
How do you know if the electricity enters your body versus just getting shocked?
we'll see that in a minute on the, okay, but that's a good question.
Do you start going like this?
Yeah.
Where do you go?
But this little cartoon next to it, it shows electrical shock pathways. Like if you grab onto something high voltage, it'll show different, depending on where that thing hits you or starts, it'll take these pathways through the body. You see the little guy with the sad face, right hand to left hand, down to the bottom right corner, left hand to left foot. Those are pathways that go through your heart. And that's basically what will kill you with electricity. Right foot to left foot or right hand to right foot, they'll hurt you still. You might get burned and stuff, but they're not likely as likely to kill you. But when it goes through the heart, that's really what's dangerous. And as we just said about your skin being wet, insulators can become conductors if you add, for example, water. Mr. Laraway thought that was snow, but that could be snow, paint or varnish, wood preserver. So you can't just assume, well, it's wood and that's a good insulator. If it's got paint or varnish on it, it can be conductive. So those are things that it's kind of tricky, but yeah, they can change. So here are the effects of the electricity on the body, which you were asking about. And this is measured in milliamps, which is 1/1000th of an amp. That's a very small amount of electricity. But you see on this chart, a little more than 3 milliamps, you're going to get a shock, a painful shock. More than 10 milliamps, your muscles are going to contract so that you cannot let go. So if you grab something that has, more than 10 milliamps, your body, your muscles like cramp up. And if you're holding on to that, you're not going to be able to release your muscles because that's the effect it has on you. More than 30 milliamps, you go through lung paralysis, your breathing stops. 100 to 200, you go into ventricular fibrillation. That's where your heart stops beating. It just sort of quivers. And when you see, I know you've all seen programs or whatever where they get out those paddles and they shock your heart. That's called a defibrillator because it's going to take that from fibrillation back into a regular heart rhythm. But most fatalities are caused by that fibrillation. Over 200 milliamps, you can get severe burns and your heart can shut down, but oddly enough, that may actually save your life because it's the fibrillation that really kills you because your body cannot pump the blood anymore. The amps pose the greatest danger of electrocution, but it's volts plus amps plus resistance that determine the level of harm. So, some people think, well, this is just low voltage, it can't hurt me. Well, it can, depending on the other, factors involved. And all these things have to do with 120 volts of alternating current because we know alternating current is what is in our homes, in our outlets. It's what we deal with all the time. So what do you do if you come across somebody who's being shocked or electrocuted? Well, the first thing is, if you can, just stay calm. And that's hard when you see something being electrocuted. But you just don't want to rush in because your first impulse is to go and grab that person. And you do not want to touch them. If they're still being shocked, you need to have them disconnected first from the power source. Because if you touch them, you will become part of the electrical path that's killing them. And you also could die from trying to help them. So don't rush in. You do want to turn off the power if you know where the disconnect is. Now, here we are in the church. What if somebody had their hand over there stuck in that outlet and you wanted to disconnect the power? How many of you know where the power panels are in this building? Okay, some people do. Most of you don't. If you're going to run off and try to find them, and they may be in a locked room, your person's going to die before you ever find your electrical shut off. So,
And you'd be surprised. So we actually have 5. Nope. We have 6 panels in this building.
Yeah,
And
6 panels.
And they're all in different locations. Well, 3 of them are together. Every other one is in a different location.
So,
3
which
separate.
panel would you turn off? Which one would you know to go to? Which breaker do you know to turn off? If you don't know all that stuff, like right up front, it's better to go to plan B, and that is to try to get them pushed away from that
Just beat them with a bat.
power source. Now, if they are and you want to use something that's dry, something that's clean, something that's non-conducting, like wood or rubber. You're not going to take a metal chair and try to push them away, because you'll just get electrocuted too. But you either try to knock them down. I mean, it sounds mean, but you're going to knock them down, or push the wire away from them to try to get them separated from that power source. Never try to rescue someone near a high voltage line. If you are outdoors and you see downed power lines, you should never get near them. Some people think all down power lines spark and spit and jump around, but that's not true. They may look like they're harmless, but you should never get near them. You should call your power company, either DTE, I guess is what you have here, or Consumers Power,
We have consumers.
depending on where you live. So yeah, you should call 911, report down power lines. So if there's somebody over there and they're being electrocuted, you cannot rush in and help them on a high voltage line. You just need to call 911. Now, if you have somebody, they're done being shocked, you came upon them, they are laying there, they got shocked, and they're conscious, you can help them. Well, number one, you don't give them water. For some reason, that can cause a stroke. I don't know the medical explanation for that, but they say do not give them water. And it's good to place them in what is called the recovery position, which is what that man is there. Roll them on their side. It's to keep their airways open so they can breathe. You want to stay with them until they arrive. You don't want to just roll them over on their side and go home. Try to stay with them. And be careful. If they may be bleeding, electrical shock can cause bleeding. And I have here, how many of you taken first aid class? Okay, so you want to follow the instructions on your first aid class about handling blood, stopping blood flow. You know, if they look like they're bleeding to death, you want to try to stop that. But they always warn about, contamination, contact with blood. Now, if they're unconscious, you find them, but they're not being shocked anymore. First thing is you should just assume the worst, that they're dead. Because even if you tested their pulse and they're like, well, I think they're dead, like we just saw a couple of slides ago, that means their heart is stopped, but they may still be able to be resuscitated. So if you know CPR, you can start CPR right away, because I say they may be just mostly dead, and that just means their heart has stopped. But an electrocution victim whose heart is stopped may be saved if treated right away. Now, the key word there is may. It's not a guarantee, but they may be saved. So, because the heart actually stops to prevent the fibrillation, that quivering of the heart. But so it may be possible to resuscitate them at that point. Now, say you're the one getting shocked and you grab something and you cannot let go. They say to try to let your knees collapse, let your body fall back, and the weight of your body can pull you away from that electrical wire or whatever it is that's causing you to be shocked. So, now, in all cases, you should seek immediate medical care. So you need to call 911 as possible. Hopefully, if you have somebody else with them, they can call 911 while you're trying to help the victim. But, you kind of have to prioritize. It's important to get them away from the shock, the power source before you call 911. But you need to call 911 as soon as possible. And here's just some tips for calling 911. Just make sure you let them know your exact location. If you're in a building, you can say, well, I'm out at Faith Baptist Church. Tell them where you are in Faith Baptist Church, because, they don't know our building. You've got to say, well, I'm downstairs, And if you're outside, you need to kind of give them the best instruction you can to where you're at. Let them know what your emergency is. Try to stay calm, speak clearly. If you've ever heard a 911 call, it's some people, people get frightened, and I understand that. So you've got to try to stay calm. So now we're going to learn about safety around the house. The most dangerous place you can be is in your house. They say more accidents happen inside the home. You never want to stick a foreign object into a receptacle. A screwdriver. Now you think, well, why would I stick a screwdriver in there? Well, you might be trying to put on an outlet cover and slip, and your screwdriver can go into there. So, you don't ever want to do that, because there's 120 volts in there and it can kill you. You don't ever want to stick an object into an appliance that's plugged in. You see the guy there, his toast didn't pop up. He's trying to dig the piece of toast out with a knife. Has anybody done that before? Mr. Laraway did when he was a child. But you don't ever want to do that because there's electricity in there, you know, and that's dangerous. So there are electrical protective devices. We learned about them. You have the first ones are the circuit breakers. There's a picture of a double pole breaker up there. A circuit breaker stops the flow of electricity when it reaches dangerously high levels. So they turn off or trip. You know, did the breaker trip? You might hear that term. That happens when either too many things are plugged in to the circuit. That's a circuit overload. That's a picture of that over on the right-hand side, by the way. All those wires plugged into one outlet, that's a circuit overload. Or during a ground fault, which is a short circuit. You might have a bare wire or something cause a short circuit. The circuit breakers will trip. But what do circuit breakers protect? They protect the equipment. They do not protect people. They don't prevent electric shock. They will not prevent you from being electrocuted. And the reason for that is that regular circuit breakers are not sensitive enough to turn off fast enough to stop that flow of electricity to you. So you can't just assume, I got circuit breakers, I don't have to worry. They don't protect people. The only way they're going to protect you is if you use them by turning them off before you start working on electrical equipment, which is something you should always do. Now, we do have the ground fault circuit interrupters though, and GFIs or GFCIs, they're also called, do protect people from electricians. Or I keep saying electricians. Yeah, sometimes you need to be protected from your electrician too. But electrocution, see the little baby, he's happy. They are used to protect people in wet areas. So that's why you find them in bathrooms, in kitchens, and outdoor outlets. Do any of you have like an outdoor outlet at your house, like maybe on the porch or someplace? It's actually the code, electrical code, to have GFIs in those areas because those are areas where there's water and you need protection from that. Now, they're very sensitive, so even though they work good and they turn off easily, they also kind of trip easily. So you kind of need to check them every once in a while. You can't just say, well, we have them and we don't have to worry about it. Mr. Laraway calls it exercising the breaker. Sometimes you just need to go around and make sure that your GFI outlets are still on and haven't been tripped, and you kind of push the button off and push it back on, kind of reset it and make sure it's working. They're not always found in older houses. We've bought several old houses we fixed up, and old houses don't have GFIs. They didn't have them back in 1870 when your house was built. So unless it's been remodeled, you may not have them in there. So you just can't assume every house has them in there, even if it's been remodeled. The house we bought now had GFIs put in, but they wired them wrong, so they were not useful. So they would not have protected us from electrocution if Mr. Laraway had not fixed them. They don't protect every circuit of the house. The only things that are protected with a GFI, like an outlet or breaker, are things that are connected to that circuit. And those are usually your circuits in your bathrooms, in your kitchens and stuff. They're not usually hooked up like to bedrooms and family rooms and living rooms. So if you're in your bedroom and you decide your feet hurt and you want to put them in one of those water spa things, and then you put your feet in there and you plug it in, you could be electrocuted because there's not a GFI probably protecting that circuit. So you can't just assume everywhere in your house you're protected from that. And they are important because most fatalities involve the 120 volts, which is the voltage in your home outlets, which is the current electricity that's in your house because it's on the current is flowing on your circuits. Now, we also learned about static electricity. Now, how many of you have ever rubbed a balloon on your head, made your hair stand up? Okay, that's static electricity. If you walk across the carpet and touch a doorknob, you get a shock. That's static electricity. Static electricity is, I don't know if we've learned this yet, but it's when electrons build up on the surface of a non-conductor when they get like rubbed together, but they're just sitting there waiting to get near a conductor. And when you get near a conductor, then they discharge, and that's where that shock comes from. Well, we think of that as being, well, it's kind of funny, it's something you do at parties or whatever, but there's also dangerous static electricity. One of the most dangerous static electricity items is lightning. Lightning is caused by static electricity. It's a giant spark of electricity in the atmosphere between the clouds, the air, and the ground. Lightning can have 100 million to 1 billion volts, or contain billions of watts. So we all know lightning is very dangerous. It can strike miles away from the storm that produced it. So you can be outside, clear blue sky, and still get hit by electricity or by lightning if there's a storm 5, 6, 10 miles away and the lightning follows a certain path. Don't want to make you afraid to go outside ever, but if you are outside and you hear thunder, because thunder is the noise that the electricity makes when that lightning discharges, because it like breaks the sound barrier, I guess. You need to take shelter, and we all know you don't go under a tree, you don't stay out on the golf course with your umbrella up in the air. You try to find the best places indoors, because it can strike you. And I may have this later on a different slide, I don't remember, but even indoors, lightning can get you, because if it hits your house and you don't have that ground rod, it can hit your plumbing, and it can get you at the kitchen sink. It can get you in the bathroom if you're taking a shower. You really shouldn't shower or wash dishes and do anything with water during an electrical storm because of that. You also should not be dealing with electronic devices and stuff. You shouldn't really sit at your computer during an electrical storm. I know we all do it. This is a rare occasion, but it can happen. And even a small spark can be dangerous if it's near flammable or explosive materials. It can cause an explosion. And how many of you deal with flammable, explosive materials every day? What do you think? Okay. Oh, you think so? So Peyton, what are you dealing with that's flammable and explosive?
Gasoline. I deal with a lot of gasoline sometimes.
Yeah. Well, some of us don't think so, but think about gasoline. How many of you drive a car? How many of you have ever gone to the gas station, filled up your car? Okay. You have to be really careful when you're using gasoline. Now, we know if you throw a match on gasoline, it's going to ignite, but it's the fumes that are highly flammable, and they travel quite a distance. So you can have static electricity from getting in and out of your vehicle. Every time we get out of our car and touch the door, we get a shock, because we've built up static electricity sliding across the vinyl seats. So when you're refueling, you should not be getting in and out of your car, because that little spark can ignite the gasoline. That's why they tell you, not to be getting in and out of your car. You should never fill your gas cans inside the vehicle because of that. You should always have your vehicle turned off, because your engine produces sparks. You have spark plugs in there. That could cause an explosion. You shouldn't even fill a gas can in the trunk of your car or in the bed of a pickup truck, because if that explodes, well, it's going to blow up your whole car and maybe a lot of other things. And you see these signs over there. When you go to the gas pump, there's all these signs about no smoking, don't do this. The reason they're there is because it's a real and present danger. It may be a rare occurrence, but it still is a present danger. So we're trying to teach you to be safe here. Now, if you're going to work on electricity, there's a lot of distractions that can get you not being focused on what you're doing. And so one of them is your friends. And if you're trying to work on something electrical and your friend's there and they're trying to get your attention, or they're horsing around and you're trying to work, it can lead to a disastrous, deadly situation. Another distraction is music. Music is processed in a different part of your brain from work. So I know everybody thinks I can listen to music, I can multitask, but scientific studies with electrodes on people's brains have shown that you cannot really, your brain really cannot multitask like that, because when you have different inputs into your brain, like music, and you're trying to think, your brain basically divides those functions up, and you really cannot give full attention to either one. So it's a fallacy that you can listen to music and still do your work and be focused on what you're doing. So it makes it hard to concentrate, which is another reason talking and texting is a deadly distraction. So pretty much anything you would think about driving, we know it's against the law to talk and text, because same thing. You cannot be talking on the phone or texting somebody and still have your complete focus on driving. A lot of people think they can, and that's why so many accidents are caused by people who are talking and texting. I don't know how many times we get behind somebody, they're swerving on the road, they're going 20 miles an hour in a, on the expressway or whatever. It's because they're distracted because they're talking and texting. So if you think of it this way, anything that would be dangerous to do while you're driving would be dangerous to do while you're working on electrical problem. Extreme emotions, good or bad, happy or sad, they make it hard to concentrate. So if you just got like a scholarship to your chosen university and you're just excited about that, if you just, well, you're too young for this really, I guess, but if your girlfriend just says she'll marry you, or if you just, or if your dog just died and you're really upset, those emotions distract you, and that's not a good time to go and work on electrical work when you're in an emotional state, either a good one or a bad one. Also, overconfidence, thinking I don't have to read the instructions, I've done this before, I know how to do it. Most on-the-job accidents involving electrical ones involve employees who have been doing electrical work for over 20 years. So we have a quote here by Neil Armstrong, you know who he is, right?
Have snacks and stuff set up whenever you're ready for a break. I have snacks and stuff set up out there.
Oh, okay. The pieces here?
Snacks.
Oh, snacks.
Yeah.
You're going to have snacks and lunch?
Well, generally, we take like a break every hour or so.
Oh, I'm overdoing. Okay, yeah. Okay. He says there's snacks set up, so we're not going just yet. I'm like, well, we're having lunch, but I guess he thinks your brains need a break in here. Okay. So Neil Armstrong, you know who he is? Everybody know who Neil Armstrong is? Does anybody know who Neil Armstrong is?
Yeah, we know.
He's an astronaut. He walked, I believe he walked on the moon. This is a quote for him. Well, I think we tried very hard not to be overconfident, because when you get overconfident, that's when something snaps up and bites you. Overconfidence can lead to taking shortcuts for safety. You don't ever take shortcuts. You want to follow good safety procedures. And this is always the procedure you should start with before beginning electric work. You're going to test your ticker with a known working receptacle. Now, we actually have tickers for all of you. Yay! We got giveaways today.
Oh, those are
Courtesy of the church and Pastor Summers, really. Whoops. Why don't we give you? We'll give you each one, and Mr. Laraway here is going to just show you how this works.
They come with an instruction sheet.
Huh?
They come with instructions.
Yeah, well, Mr. Laraway is still going to show you how this works, even though they come with instructions. He's just trying to get out of work. He doesn't understand that. Okay.
Are you going to finish that up?
Now, I want you to show them how to use the ticker first.
Oh. They're called tickers because some of them actually make noise. When you get close to the circuit, there's a little on-off button.
I think we found it.
Some of them just get carried away because you have so much electricity in your body. I think I have a defective one. Well, it has a light. That's pretty cute.
Well, like these guys are all beepers, so we should call them beepers. So tell us, why are they beeping?
Well, they're beeping to indicate that there's
No, they mean over here.
oh, just beeping with nothing.
Keep hitting the power button is what it is.
Yeah, mine doesn't. I'm gonna use my own. This
Well, the body does have electric current in it. You know, your body does produce electricity also.
How would you find that?
That's what it's supposed to do.
Oh, oh, you hit the button, it turns on and off. Hit it, we go inside, there's a light
That's what a
on.
power button.
No, I think I pressed the right one.
Well, they're supposed to light up and tick, so it indicates that there's voltage.
So I guess the first thing you need to do is make sure you have a beeper or a ticker that works.
Yeah.
So don't just assume your ticker works, because actually they run on batteries, and maybe the battery's dead on your ticker. So you might,
How do you get your ticket check for the?
Yeah.
You hear the X?
yeah. So you might hold it and say, oh, it's working.
It works, it's just not very loud. Okay,
So before
That's enough for
beginning
ticker.
any electrical work, okay, guys, pay attention. Before you start any electrical work, make sure your ticker works. And then you want to test it on a known receptacle. So if you've got a lamp plugged in and it lights up, you know that that receptacle's working, you can test your ticker there. Then you want to go turn off the correct circuit breaker. Then you want to come back on and back in and make sure that that actually turned off, because like Mr. Laraway said, he has had situations at work where people said they turned off the power and they actually didn't turn off the power.
they thought they did.
And he was actually one time on a ladder and got shot off the ladder. And if he hadn't had safety glasses on, he would be blind today, because that one, when he bit into that 480 volts, it exploded and shot copper into embedded it in his safety glasses. So, yeah. But so you want to follow good safety procedures. And here we talk about this. Don't rely on others to turn power off for you. I like this little here, the house is on fire. The little girl says, they said to turn off the stove, they didn't say when. So don't rely on others to do it for you. Don't rely on labels. And it's not that other people are incompetent or anything, but maybe they went to the panel and it wasn't labeled right and they thought they turned off the right one. And, you know, and sometimes you think, well, I'm in the living room, so these are all, outlets are all on one circuit. Well, not necessarily. You want to use good lighting when you're working on electricity. Now, you might have to get on a ladder, so you have to know good ladder safety. So you do not want to use a metal ladder when you're doing electrical work, because it's a conductor and you could get electrocuted. So you want to use either fiberglass or a wood ladder, but it's got to be one that's clean and unpainted, you know, because if it's got dirt or paint on it, it could be a conductor surface.
The whole thing has to be fiberglass?
Hmm?
Like fiberglass edges and metal steps? That is
Fiberglass, yeah.
Maybe that comes to fiberglass.
That's, yeah.
That's ideal. They have an entire fiberglass ladder.
So if you have a step ladder, you want to make sure the ladder's open all the way, that's locked in position, that is on an uneven surface. I was doing some trim work in one of our houses, and I was on a step stool and it was on carpet and it was not stable, and it flipped out from under me and I fell and broke my ankle. So yeah, you want to make sure that your ladder is stable. You want to check above you for hazards. You might have lights, power lines, depending on where you're working, ceiling fans. Those are all things that you want to make sure aren't above you when you're working. And move your ladder if necessary. Now, there are some people, I have seen them do it. The ladder's not in the right place, so they'll just kind of jump up and down and bounce, try to bounce the ladder over. That's not the way. Mr. Laraway's covering up his head over there.
What?
Don't lean or stretch. That's another thing. That's probably one of the reasons I fell and broke my ankle. I was leaning and it was unstable and I fell. So that's not good ladder safety. You want to dress properly. So you don't want to wear loose clothing. And the reason for that is you might be working around equipment that has, you know, gears or something, and you might get caught in the equipment, or you have a loose shirt or something, it might get caught on the ladder, it might cause you to fall or whatever. You want to keep your skin covered. You see those notices, no open toe shoes or flip-flops or sandals, no shorts, no t-shirts, short sleeve shirts. You want to wear long sleeves, long pants. Mr. Laraway has a experience he can tell you about having a short sleeve shirt on doing electrical work.
I was working on a ladder, a suspended ceiling similar to this, and there was a pipe with wires in it, and I had my elbow on the pipe, and I'm working with the wire nuts, and the wire nut was not installed correctly, and my finger touched the 277 volts from here to my elbow, and I had to just kind of let go and slide down the ladder.
Well,
Because
yeah,
I
that
had
was
short
burned.
sleeves. Yeah, it hurt.
Yeah, your little burn.
So you, if you're going to do electrical work, you really need to have long sleeves.
Your skin covered up, and you know, especially because if you're working hard, you might be sweating, and it's not your dead skin cells are not going to protect you because you're conductive now. You want to dress properly. You've got to, remove your watches, rings, other metal objects. When you are an electrician, it's the law, is not, Mr. Laraway? It's the law that you have to take all these things off.
Well, company policy.
Now, he has told me about men that he knows about that wore their wedding ring on the job.
I've seen videos of men that had their wedding ring, they took their finger right off.
Yeah. So the skin was okay, but it hit the ring and it actually blew his finger off because that circled his finger. And if you are PBR winner and you got your big belt buckle from winning the bull riding contest, it's best not to wear that on the job, but if you have to, you need to keep it covered up. This guy doesn't have his covered, so he's not being safe. And there is actual protective equipment that you are supposed to wear. Insulated gloves, plastic safety goggles, different protective. If you're dealing where there's arc flash, don't you have a special protective you have to wear for
When you're
that?
working on voltage over 480, you have to have shield glasses, shield, special gloves. But your clothing has to be arc flash rated. The higher the voltage, you need a lot of high specialized equipment.
So we all should know water and electricity don't mix, but we don't think about it much. If you're handling tools or equipment, power tools, power equipment, you want to make sure your hands are dry. And they're, again, not sweaty. And we need to make sure your hands are dry. You want to keep your work area dry, the floors, the workbenches. You don't want to have a can of pop or a bottle of water or a cup of coffee there in the work area. And keeping your gloves and footwear dry, because it's just, water is a conductor and it's not a good thing to have around electricity. And as we said before, the insulators can become conductors if you add water, dirt, or paint or varnish or whatever. Now, using tools and equipment, you want to choose the right tool for the job. So when you're doing electrical work, you want to use non-conducting or insulated tools. These are all insulated tools. They have rubber or plastic handles on them.
These particular tools are insulated to 1,000 volts.
You want to check your tools for equipment or damage. You want to check your switches, the cords, missing parts. You shouldn't use tools that are damaged because they're dangerous. You want to operate your tools and equipment safely. You turn off equipment with a switch, not the cord. If there's a switch on it, that's what you're supposed to use. And you're not supposed to plug tools into a damaged receptacle. Extension cords, now we all use extension cords, so you want to make sure that they're not damaged, the insulation's not damaged on them, the wires aren't all frayed like in the picture there. And if it's a 3-pronged plug, you want to make sure that that ground prong is not missing. That's the thing that helps protect you from mishap. You want to choose the right extension cord, so you want to look for cords that are UL approved, amp rated for the job. So explain the amp rating there.
If you are running a power tool that draws a lot of current, you need an extension cord that will handle that current without giving you a voltage drop.
So I'm sure you've seen little ones like for a lamp, a lamp. You're not going to use that with a generator.
You know, 6 amps, and you're going to put a 20 amp power tool in it.
It'll overheat.
It's going to warm up.
And here's one, it's hard to understand, but you should not use adapter plugs. If you just have 2-prong outlets, you should not get an adapter that you can put a 3-prong appliance in and then stick that into a 2-prong thing. If you go on the internet, they're for sale everywhere. But the reason they're not safe is because only the plug is grounded. If you have a 2-hole receptacle that's not a grounded receptacle, plugging in a grounded plug is not going to make it grounded. It does not protect you. So you can be electrocuted doing that, and they sell them everywhere. So it's a little bit misleading when they say, well, this is a grounded plug. Well, it's only grounded if it goes into a grounded outlet. So that's why you shouldn't use those. Also things you shouldn't put your extension cord over, like a hot pipe, because it can melt off the insulation. You don't want to leave it out there where you can trip over it. You never want to run an extension cord underneath the rug. There again, if you go online, you can see all kinds of ways you can do that, but if that cord gets worn away or damaged under a rug, it can cause a fire or an arc flash, which Mr. Laraway explained what an arc flash is.
Well, that's the instantaneous current when you have a wire short together, it arcs. They have new circuit breakers now that will eliminate that arc.
Yeah, in fact, some places it's the code now to put arc flash breakers in, but a lot of houses aren't going to have them. It's very dangerous. Extension cords are not permanent wiring. So you notice here in the picture, the black plug there goes through the wall. They're using it like wiring for the house. That's not. And we have a niece, we went to her house, she was having some electrical problems. Her whole house was connected with extension cords from one room to another, then plugged into a power strip and then off to another thing. That's not what extension cords are to be used for. We told her she was going to burn down her house, but she still probably does it. And you do not want to unplug by pulling on the cord. You always hold it by the plug when you unplug anything, whether an extension cord or a regular cord. The buddy system, if possible, don't work alone, because a work partner can be helpful They can alert you to hazards. Maybe you didn't see that thing overhead, or they can hold your ladder steady, or say that I do. Here's how I help Mr. Laraway in the buddy system. He sends me off for tools. Oh, go get me the hammer. Do you know where the So I run and get the equipment for him. Also, helps you prevent the temptation to overreach on your ladder, because somebody's there to help you. They can answer the phone, the doorbell for you, and they can summon help if you fell off the ladder, got electrocuted, or whatever. It's good if you have somebody else there to help in that case. Knowing your electrical panel is important. You need to know where it's located. You need to have your circuits labeled correctly. You need to be familiar with where the breaker locations are, especially on a big panel. You want to use breakers designed to work with your panel. In other words, the same manufacturer. So, like if you have a square D panel, you don't put in an ITE breaker. And you don't try to modify those to match your panel. That's actually against the law, and it's very dangerous. People do it, but a lot of people do things that are not correct and are dangerous. So you never block or store anything. Actually, it's the law within 3 feet of a panel. You're never supposed to, use the panel for storage. So you see electrical panels open and there's screwdrivers in there, or a bottle of water or something. It's not a storage cabinet. You don't ever leave that panel unattended with the cover off. But there again, you guys should never have a cover off a panel because it's dangerous. And you cover any of those. We showed the knockouts on that little panel where the breaker shows through. You never have any open slots there. If you do, there's special seals that go over there, because otherwise that thing is open and you could, put something in there. You need to learn to recognize hazards, like there again, frayed electrical cords, broken light sockets, damaged switches, and on things that are installed, exposed wiring. All electrical boxes are supposed to have a cover of some kind on it. You see that one in the wall with all those wires hanging out? It's supposed to have a cover on it. Too many things plugged in. Those are all things to watch out for. And those are things you can see outside the wall, but there are a lot of hidden hazards inside the wall. And we're actually going to see those in a minute, because Mr. Laraway has something coming up to show you that. And cutting into the walls can be dangerous too, because if you're going to do remodel work, you might have to cut your wall open. You don't know what's in the wall, so you just can't start cutting in with a big saw into the wall, because there might be gas lines in there, ductwork, water lines, other electrical lines. If possible, it's good to have a blueprint, but you hardly ever have one, or an as-built drawing. That's where somebody has changed things and they wrote down what they changed, especially if you're buying a house, working on an existing building. Now, a place like this, the church, is going to have blueprints, but a house, you're probably not going to have the blueprints, so you need to check carefully. You might have to open it up, but you open up a small section of the wall. Or if you have a basement or attic, sometimes you can go up there and see where wires come down and kind of locate things, but, not always. So we have now, coming up right next now is, we're going to have, before we do that, Pastor Steve needs a snack. So he's got a snack ready for you. So
Go stretch your legs, go to the bathroom.
yeah. Because Mrs. Laraway will work you to death. Mr. Laraway will tell you that. So
We have 2 call-ups. The hospital told me right here, like, hey, can you come in? Like, it's double time if you come in.
Surprised you didn't text me. Sorry. Oh, yes.
so how long is the snack time?
10 minutes or so.
Okay.
5-10 minutes.
I don't have this figured into my time frame here,
You expected him to go for 3 hours without a break?
Yes.
People have to pee. I mean.
They should go before they come. No.
And then hold it for 3 hours.
It's okay. But we're on schedule right now,
We are.
except for this 10-minute thing, but you know.
Well, the good part's coming up.
Because, you know, I went through all of our, you know, notes and videos and everything from the last time, and I thought, okay, they took like from 10 to 2:30 both times. That's like, no, that's like 8 hours, and even minus the half-hour break, that's still 7 hours. And how am I going to do all this in like 5.5 hours? You know?
And we went through it, it started getting smaller.
But we did eliminate just a couple of the demonstrations that were just for fun. Well, everything is.
Then I get up there by Michael's blank.
Everything is instructive. Yeah, he's
Just
like
went-
he's a blank.
It just went blank.
So that's why hear the voice from the back of the room. Oh, okay.
Well, you know, she's been doing this for 50 years too. I mean, seriously.
And I knew that this thing was long, and I didn't want it to be like
Longer.
hearing the missionary videos. Even though I'm sure that's what it's like to them. It's like, oh, a half hour of listening to this safety stuff. But it's necessary. It's a necessary evil.
Right.
All right.
I couldn't get that ticker to work.
Was one of theirs?
Yeah.
Oh.
Wouldn't do anything. Well, I guess I'm gonna go off and get
It was pretty bad when the electrician can't get the ticker to work. I'm sorry, what's your name?
Noah.
Noah?
Yes,
It's
sir.
nice to meet you. We had the introductions before you got here. But
Oh, yeah, well, we always, try and get here earlier than life happens and
Yeah,
get here
yeah.
like right on time.
The last few times, like even coming to church, and we leave early, it's like we live in Jackson, so like, oh, there's construction, and then all of a sudden it comes to a stop, like 2 exits before you have to get out, and you're just sitting there in traffic, and like, oh.
Yeah.
So,
Yeah. So,
You didn't miss it. Well, I explained to them before you got here, this normal.
yeah.
So we have
Yeah, yeah.
Oh, we started.
Yeah.
We're just doing introductions.
Yeah, you guys are going to the sheet, right? You guys are going to the sheet
We're going basically.
for the test. I'm out of the sheet, right?
You are.
Okay.
And like, especially like I explained to one of the students who asked me a couple days ago, what kind of nervous about this class. Is there going to be a test? I said, there's 2 tests because it's only a 2-day class. So now there's 2 tests and 2 projects that you don't have to pass. But our purpose is not to fail you or to see how hard we can make it on you.
Yeah.
We want you to have some things in there that
Yeah.
you have to think about, but it's very
Yeah, see, I've done some lights before, but then, I can do more kind of electrical, but it's just, I don't know any, word about Verizon,
Well, we know that the videos from the engineering mindset as an electrical engineer, we know that they're complex. I mean, so we don't expect you to memorize all that. I haven't, because I'm not even an electrician.
right? Yeah,
I'm just the electrician's wife. But we just thought, that to just jump in and say, well, here, wire this up, that is not good if you don't know exactly how the electricity works. And, we just like to give you a whole overview of electricity. And that's what those videos are for. So I know you're watching it and probably, even on the video, he says, if this is too hard, don't worry about it, there's another video. Yeah, so I don't want you to freak out. There's big tests in here.
Emily, of course you can.
There's a liquid.
It is your last day in class. How's it feel?
And I don't know, I'm not the
Kayla,
one
how's
who
it
sets the,
She's gonna miss it.
I'm probably gonna.
You're gonna miss it.
Once we wrote the test.
You're probably not what?
I said it might come back. It's Olivia.
You guys just get this?
Yep. Again. It's not really functioning correctly yet.
Oh, okay.
But this is-
That's DGI rebooting. It's booting up and stuff. I understand.
But I said, I will look at you all.
I'll use it a little bit today. But
If you take any photos, could I take that SD card home? For your book?
Yes.
Okay. Okay, sounds good. I brought my camera as well, so I'm hoping that when he's showing us the I put like boxes and stuff like that and all that stuff. Yeah, when you do your hands on, I'm really looking forward to that. That's maybe what
Soda,
your hands on.
Gatorade.
Gatorade.
Depending on the time.
Yeah, I've cut like 4 or 5 times.
Bro, I'm so confused. How are you looking?
Well, I don't know, like, I'm not an Apple guy.
It's 69 right now. I can turn it up. What do you want up to? You want it like 70?
Just turn it down to like 65.
This is all I do.
You have a hoodie on.
I just took it. Yeah.
So no.
Just see what it does. That's why I put the phone pin on the bottom. I was in service one time. It was always right here, and I accidentally hit it during service, and I'm like, oh, weird.
I know. So that's where I thought I hit, but the funeral home told me, or the hospital told me.
It's different. It's different. I thought someone was around me calling me, and at first I thought to myself, I go and watch this. I thought someone did. It's actually done at two places. This month, that month. No.
Well, I already had my phone called 71.
No, she didn't.
Yeah, she did. And then the answers were like, oh, what's your emergency? I'm like, oh no.
Who's Irish?
Hello, squirt.
She's 3.
Yeah, I've called 911 accidentally like 5 times in the last 2 years.
What are you doing?
Become the stereotype for me.
Oh.
I mean, you throw it in your
So,
pocket and all of a sudden.
I was working with my dad in his bedroom. They were remodeling the bedroom. My dad set the phone inside the window, and then I opened the window, and I forgot that his phone was there. It was in a tough case. And I'm like pushing, and I look over, and I hear and it's calling 911. Because if you hit the buttons,
Yeah, the stupid iPhone setting.
if you hit the buttons multiple times, it'll call 911. I think it's the volume up button, like.
Yeah.
You guys want to test that theory out right now?
Or the volume down. Yeah.
I'll go down, you go up.
Okay. I'll go.
If you do that,
Alright, here we go.
if you push both of these.
Oh, no, I think they're all gonna call out.
Do you have that SOS? What?
Yeah.
Oh, wait, I think it was the.
I think so.
Oh,
I got
volume
some weird
down
settings.
and
That keeps on
power.
happening to me. It's annoying.
It ain't working.
No, you can slide it off.
Yeah, right here.
Yeah.
Oh no, if you hold the button.
Yeah, but like I called it, I was shoveling. Okay, I was getting.
What?
How do I out the manure spreader?
No, this is
I pulled 911 out of my pocket. And so
You know what?
Police brother shows up at my door. My boss is like, what? Where's the lock? It's like, I don't know what happened.
That's what Neil Armstrong
And then I don't know the address.
Okay,
So they
everybody's all
asked me the address,
refreshed
they
now?
gave it to him.
He took a selfie stick.
So here's Mr. Larry's wall of shame. And what this is examples of, especially if you're going to work on older buildings, of things when you open up the walls, you may find these are all either code violations, because there are electrical codes that cover everything.
Some of the stuff was in my basement.
And some of it is, are just safety issues, but most codes, or probably, most codes are put in place because of safety. Because, there again, as they keep saying, we keep saying, electricity can kill you, so it's important to do things right. So we've got them all, we know you can't read that, he's gonna let you know what they all are though, so.
Okay. These are, like Ms. Laraway said, examples of stuff that we've actually seen And it's only touching the tip of the iceberg on the violations and idiotic things that go on inside people's walls that people try to get away with. Someone ran a piece of Romex, which is the wire used inside walls. Just instead of putting a box, they poked a hole in the wall and put an extension cord end on it. Mrs. Laraway has been doing electrical work almost as long as I have.
So when he says a
Don't
box,
let her fool you that she doesn't know what's going on.
this is a box. And anytime you run a wire through a wall, you have to have it in a box. So these people just ran it through the drywall. We've seen this before. Actually, we have some of this in our basement right now that we have to fix. But so go ahead.
But you never know what you're going to get
You're not.
when you get your house. So you have to look around. The code violations will jump out at you after a
So
while.
you're gonna go. Don't jump around. Go top to bottom.
I'm going to go top to bottom. All right. Buried junction box. It's against the code to have wires in a box and then drywall over it. Because if you have a problem, how do you find it? Well, except for taking the drywall off and finding it, there's no way to do it. So it's against code to have a box buried in the wall.
And a lot of times, like you'll have a problem in your house, you can't figure out why can't I figure this out. You find out because they've buried stuff in the wall, and so that's just. And sometimes
We were working at our niece's house trying to find she had some problems. And I ended up disconnecting more stuff than I connected because it was just illegal. And I had some outlets that were not working over there. The panel was over here, and they had put paneling over a wall, and somewhere they covered up a box. So unless you're going to rip off all the paneling, there's no way to find it.
sometimes even in a new build, because the electricians, because they have open walls, they put the electric stuff in there, and then the drywaller comes along
Right over it.
and drywalls right over your thing. We had that down in Georgia, helping a missionary, could not figure out why this one circuit, where'd it go? When that happens, you look, there's usually a bulge in the
Yeah,
drywall.
if you can
Where
get
they
to
went
where
over
you
the
can
top of the-
look down the wall.
Yeah, well, we never did find the one, they're just, because they buried it, and that's illegal, but it happens.
So,
And there's no cover on this box either.
no cover, there's no knockouts, the wires just go, no connector, like on top of that box.
Yeah, this, I don't know if you can see it, but there's a little connector. And what that does, that protects your wire from this insulation
Bounced
being
against
stripped
the
off.
side.
Because if the insulation is off, you're gonna have a short.
And if there's a short, you don't want a spark coming out, so you want those holes filled. All right, next is no cable connector. No wire, no wire nuts. They're just, this could get shorted against the box. So it's just,
We haven't shown them wire nuts yet, but
oh yeah.
every wire has to have a wire nut on it. That's the code. You can't just leave wires hanging out because there's nothing to protect from the electricity. I mean, if that touches there again, it can shock you. And,
No wire nuts.
Yeah,
Just
no.
did it, okay.
no, there's more than one.
Oh yes, there's low voltage telephone wire, and you're not supposed to mix voltages. So if you've got a telephone, you're not even supposed to run it through the same hole in the wall.
Yeah.
People do.
So it's okay that there's a telephone wire in the wall. That's not a
But
violation.
they have it up in this box that has high voltage.
But you can't put it in a box with a high voltage.
So they have like your boxes that have like
They're split.
okay,
Yeah, you have a box for high voltage. There's a
like HDMI or something
Yeah.
of that nature, like
Yeah.
speaker wire.
so it's a combined box, but there's a plate between the two.
Interesting.
And usually the side that has for Cat 5 has no back on it.
Right, wide open.
Yeah, so you can get the wires in and out. And they can be, because you can get a cover that's a switch, a receptacle, and it has a place for your HMDI cable or whatever. So,
That's what's wrong with it.
and what's wrong, here's a wire that's been skinned. Somebody tried to strip it and then they tried to tape it up.
Stuck in the wall with some tape. We left this. Sometimes they don't do a good job taping, but even if they do, you can't have that. That's a violation.
So if you were to come across that, you have to take that wire out and replace it. The other thing here is the drywallers are good at this. They'll come, the electrician are supposed to drill the holes as much as humanly possible in the middle.
Of the stud.
Middle of the stud. They did not, for some reason they couldn't get it in the middle, so they too close to the edge, the drywaller ran a screw right through the Romex.
So whoever did this, sometimes that does happen. They need to put, it's called a nail plate. We'll show you one in a little while. There's a metal plate that you put over that. That way, if somebody, the drywaller comes in, he'll hit that metal plate instead of running the screw through the wire. Because things aren't going to work with
The
the
same thing up here for the plumber. The plumber put too big a pipe inside of 2x4, and if he had, to make it legal, he had to put a nail plate over it. So it works for him too.
So the fact that there's a screw through the plumbing really is the plumber and the drywaller messed up. But if you're doing rework or remodeling, you're supposed to investigate, see what's back there before you just start running screws through
And
things. So.
you can't see inside the drywall. So what you need to do is get it above where you're working in the attic, if you can, and see what goes in and out. And same thing in the basement, if you have a basement. You can see where the wires go in and out, except at my house. The house we just bought, the receptacles here, normally for 50 years, the wire would go straight down. On my house, there are two to three cavities over, the wire comes up and goes that way. Impossible to fix that. You have to re-drill a hole and start all over. I've never seen that before except on this house. It's like they're being mean.
Yeah.
just being mean. So, some of the other violations in the wall. Okay. Somebody ran an extension cord through the wall so they could plug in here. So, you don't want the wall on the floor, so you run it through the wall and plug it in.
Put it in the same hole as the Romex, which there again is wrong.
Well, just wrong. So if you'll notice, this is a 2-wire receptacle. This one got a little hot. Anytime you see a receptacle that's off color, there's resistance, and it's acting like a big electric heater. And this whole thing will heat up and burn down your house. So anytime you see a receptacle, again, that's toasty. That's what we refer to it. It's brown. It's too hot. There's possibility that the wire is loose. And we'll cover all that in a little while.
Or burnt. We found them like this in the wall, and the wires are burned off. We just have to replace that. But they just plugged into it, and
well, not only that, this is the 3-wire cord, the ground prong. They just pulled it out,
so
threw it away, so they could plug in and make it work. On the side, that's not toasty.
Yeah, so that's all bad. And it got this put in with a drywall screw.
Oh yeah, it's supposed to be a 632 screw. There's
Special screws you use.
and we'll show you that too.
And also, it's only on one side, so it's in there loose. It's wrong on a lot of different things. And here, you got your
telephone guy just
but they just stapled it to the front of the
They
stud.
probably knew that we're supposed to go through the hole with the Romex, so we'll
So
fix
they just
that.
stapled it on the front. But what's going to happen is but you'll see Romex stapled to the front. That means when the dry water comes along, it's going to get.
So, going on to your side, wires in the wall, they're wire nutted, but they're not in a box.
Not in the box. And, oops, they missed one.
Yeah.
So there's supposed to be a
They
wire
did?
nut on it.
Okay,
They didn't know what to do with this wire, so.
Well, they had 14.2, we'll cover that in a while. 14.2 and 14.3. They needed a piece of 14.2. They ran a piece of 14.3.
Ah,
Just ignored it.
there's a blonde hair in here. What do you think, Nick? Am I blonde? I don't know. Okay.
What's on your side?
Well, we got the wire nuts missing. We sent it back. Yeah, I think we got covered.
We covered it.
But now over here, well, there's just a bunch of stuff, and I just have on here why just defies explanation. Sometimes when you see all this stuff, you're just like, why would anybody do that? There's like no explanation for it. So
This box was actually in my basement.
yeah, this
That's a
actually
light,
came out of our house.
and they had this just screwed to a little 2x2 and just 1x.
And is this the one? Oh, I guess not. But you can see this is really old wiring, so and it's all frayed and needs to be replaced. But we also had two of these on one wall, and this one was connected by an extension cord over to this one. So that's
Our basement stairs.
yeah, and our basement stairs, so we had to fix that. So it's amazing. And our house was only built in 1958, so you can imagine when they built in 1940, 1930, 1920, you find a lot of really bad stuff. So that's
So let's
the wall
do
is
the-
well, not that. So
This is a two-sided.
it's a two-sided thing. All right, so actually, well, let's see. I guess we got time. I think we got time for 15. I think we have time for tool talk.
Tool talk.
So we're going to do tool talk.
Tool talk. That's one of my favorites.
I'm going to help Mr. Laraway with that too. When you're an electrician, you have a lot of tools that you have to use. And so this is just a few. He said when he was working on the job, he did wired houses and buildings, everything. He carried 15 pounds of tools on his hip on a tool belt. A lot of electricians at his age, they have problems with their back and their hip, and that's from carrying 15 pounds of tools.
My age,
His age, at his age. He also doesn't
happened
really.
a lot earlier.
He also doesn't really have any cartilage in his thumbs anymore from doing electrical.
You say they can fix it. I say no.
But this is just some of the tools. There's more, but these are basic tools that you use on the job. So these yeah, you can explain it.
Okay.
I'm gonna put them on the video.
When you're cutting holes in drywall, to put a add-on box, we'll get to that. This tool is excellent. I used to use a keyhole saw, which is I still use once in a while, and I'll show you. But this makes life so great.
What's it called?
What is it?
Multi-tool.
Multi-tool. We call it a jabber tool.
You call it that?
All right, home. If we call it the
His dad
scooch-
has one that is battery operated. It's sweet.
we call it the scoocher tool, but it's actually an oscillating tool. So this big stuff.
Fish tape. He's doing electrical work and you want to run wires in a pipe. You just jam this in. This was a 200 footer. It was 240 foot. But it also works good. You cut some of this off and you can just sneak it right.
Now, on your notes someday, if you look at them, there's pictures of all these tools, and one thing that we could not find for this time was a wire coat hanger. Because it's hard to find them anymore.
I've used wired coat hangers for fishing walls. Excellent. You straighten them out and put a little hook on the end and you can fish around in there and hook
Because-
two.
For one thing, this fish tape is very stiff and heavy gauge, and sometimes you can't get into those little spots with wire coat hangers. Couldn't find one, so.
Battery drill. You all know what that is? These things are so handy.
And of course, you use them with drill bits and also with screw bits, to run screws.
I use it to drill holes on the
But
other
it's a
side.
high power tool, so you don't use it on little things like putting an outlet which you're breaking.
Stake-on pliers. If you're doing like mostly commercial work, you have the ring connectors, the stake-ons. They're Anyway, this tool crimps them and quite handy. You can use it for cutting wire, but there's better tools for cutting wire. Hacksaw. So what would you do with a hacksaw? Cut plastic or PVC or electrical pipe. What?
Sorry.
Cherokee class, baby.
Yeah, go on, baby.
I just said a joke.
And here is a man-leaf tool.
Yes.
You get this was you'd need a bigger drill than that. This is an auger drill. Brand new, hasn't been used. This is for making holes through the walls and the studs.
They come in all different sizes, depending on the size of hole you need to make.
This is the man.
This is the big one.
Actually, I needed a smaller. They come in a set of 4. I needed a little one, but Harbor Freight. Yeah, you'd have to put this in a 1/2-inch drill more because it would kill this. Hammer.
Claw hammer.
Claw hammer. This is not insulation. This is to protect it from missing.
He said
Claw
it's
hammer.
to make it from falling off. I don't know.
Yeah.
You could use some new tools.
I've had this stuff a long time.
Here's that keyhole saw he was talking about.
Oh yeah, there it is.
What you used to use in the old days before they had power tools for cutting through drywall.
Yeah, because you would take it and then just saw yourself a hole.
My dad drywall saw this drywall really well.
Yeah. Well, this one.
Well, a lot of these
This needs to be
tools,
thrown
they have official names like, like we talk about Kleenex. Well, now everybody knows just any kind of tissue you call a Kleenex, but that's actually a brand name. Tools are like that. They have brand names. They have names, descriptive names, and then they have names that electricians and workmen just call them. But as long as you know what you're talking about.
This is another power screwdriver. This you can't drill holes with it, but this is great when you're putting in receptacles, the little screws. It has a light. Actually, this has all kinds of things on it that I don't use. But they're really, really one of the best tools. This thing, if you're doing receptacles. Okay.
This is his coal miner's lamp. Oh.
Yeah. Is this the one? Oh. These are real handy.
He looks like a doctor or something. But...
Yep. You can get right in there and do stuff because most it's been said that electricians are in the dark.
And they are, but it's,
I would say, like,
because
from my
actually,
experience, like a headlamp is like one of the most important tools when you're doing electrical because you always
Well,
have
you
power
get
off.
up you get up in the suspended ceiling and the lights down here.
And most times, like you kill power to them when you're working.
especially since the first thing you're supposed to do, a lot of times, is turn off the power. You don't always have power when you're working.
And a stud finder. I'm sure everybody knows how to use a stud finder.
Finds the studs, which is important because these things need to be attached to studs.
Well, if you want to cut a receptacle in here, you just well, I want it here, and you hit it, and you're in the middle of the stud. So now you've got a hole here, and you have to make a hole over there.
You know, don't get it too close to bend. Start going crazy.
I know.
This is called, it's a tapping tool. It's called a triple tap. It actually does 6. You get these boxes, or anything, especially the metals, and somebody's goobered up the threads. This tool, it's just a tap. Like it just retaps.
It'll rethread the whole
Rethread.
So.
We built a log house, and I had an inspector come, and I had a box in the wall for a light fixture. I had the light fixture right there. It said it weighed 1.2 pounds. He told me he wanted the 832 because it was a 10-pound light. No, but to satisfy, I got my I've tapped it an 832. It says, okay, it's an 832. He says, I'm coming back anyway.
Yes.
Because they get $45 every time they come out.
Okay, say it too.
And the inspectors have the last say. You can argue with your inspector, but it's just easier to do
really
what they want you to do, so you can pass your inspection and move into your house, so, yeah.
Most of them are trying to lose it.
Oh.
Okay.
That's what I'm doing.
These are cable cutters. These will cut. These will cut a pretty good sized wire. I have cable cutters that did not bring them. They're a ratcheting cable cutter. It'll cut a piece of what they call, I think it'll go as high as 500 MCM, which is like that big around. And it ratchets and it will cut off
Your finger, if you stick it in there.
or your nose.
This could cut off your finger too, but it's harder to get it in. But these are really good when you're doing silk flower arrangements.
That's why these don't work very well now. They're made to cut copper. These are made to cut copper wire, not silk
You know, you get that
flowers.
bunch of flowers and it's got that big, you know, wire thing. You just can't go through that with some little wimpy tool. So yeah, I use some of his tools. He doesn't
She has her own
always like
She
it
has
when I
one.
use.
because they're not made for cutting steel.
Hey,
Dig them out, show them.
speaking of that, where's your side cutters?
Yeah, probably in the garden.
Yeah, well,
Okay, a multimeter. Most electricians will have this in the truck. They don't carry it out when they're doing the work. And this meter is a troubleshooting tool. You want to ring out some, let's say you've got a wire in the wall and you don't know where it goes, so you can take one of the white and black and twist it together, go around the other end, and this should heat, but it doesn't. Anyway, it's the troubleshooting tool, and they make them. You can get them for like, this is hundreds of dollars, and you can get one for like 10 probably.
see, the problem
same
we
thing.
had was when we were getting ready for this, when I had all these tools in the bag, he kept pulling them out to use them.
I had to build the wall.
And I said, make sure you put them back in the bag. A couple of things you didn't get back in the bag, so.
This is a really nice tool. This will cut different size wires. But what I like about it, you see that little hole, it'll cut a screw. Let's say you have a box that's some reason it's indented in the wall too far. So you got a 2-inch screw, but you only need a 1. You can put it in here and cut it off, and you can still thread it in. You take a pair of side cutters and cut a bolt, it's going to make a point on there. You'll never be able to get it into the box. So this takes care of that.
And it's really good if you put like knobs on your cabinet drawers and the screws that come with the knobs are too long for your cabinets.
Rack them up.
That'll take care of that. See, there's a use for it. Pastor Steve's laughing. It's true. Okay,
Voltage tester,
what do you got there? Okay,
circuit tester. You plug this in. This is not wired right. Okay, this is pretty nice. I can bring it right out here. We're supposed to have 2 green lights. Gives you a combination of lights, tells you what's wrong with this. So, we have 1 green light. What's wrong with the electricity in this room? Open ground.
Try a different one.
we could add electricity in the church.
Who did the wiring in church?
Not me.
Your name's wiring.
Not me, I wasn't here yet.
Peter Seth here.
No, not mine.
You know, say it's ironic. You do know
Oh, there's a problem in the church. It could be my tester. I haven't used this thing in years. So what we will do unplug it. Thank you.
You lick the end of it, Olivia.
So we may have to do some investigation later.
And see tripping
That's
over
why he
the
needs to
cords.
sign up for the maintenance team, right?
That's right.
Okay. So now I'll tell you about this. We got wire nuts. There's red and blue and green and yellow. And why are they different colors?
Different size, different amounts of wire that you can put in it, and different size of wire you can put in it.
Yeah.
And they go from, you can get really big, like a number 6 wire, number 12 wire. This is a slick, relatively new ground wire nut. You can put, you twist your grounds together, you cut one of them off, you slide this down the other and put it on, and it connects those grounds and gives you a pigtail. And this is for a couple number 14s.
So in here, where these wires were all out without wire nuts, that's what those are. We do have a couple over here, actually, we could have showed you. And you even get like there's some really little tiny ones. You see sometimes.
Hole saw. This is real handy if you're going to run pipe. Electricians don't use them much unless they're doing a service, but this is what you do to make it look like that. They come in all different sizes, and they even come with carbide.
Wire staples. When you do new wire, new work, your wires are supposed to be stapled on the studs. They're not supposed to be all just hanging out like this. Now, when you do a remodel, you can't get at the studs, and so you may have wires out there. But when you do a new one, and an inspector comes along, these things have to be on there, and there's a way to do it. They're very particular about how the wires, if they're on top of each other, have to be flat. They can't be on end. You can't pinch the wire with it. It has to be. You have to have them ever so, what?
3 feet-ish.
From the hole.
Oh.
12 inches or so. I mean.
Within 12 inches.
Yeah, there's codes about where to put them and how far away to put them, but yeah, they can get real stinky about if you don't do your wire staple. And they have newer ones. This is just an old school one that people still use. They do have newer ones that have little pads on them. Yeah, fancy stuff.
Gimmicks. Oh, the nail plate. The nail plate prevents the drywaller from running the screw into your electrical or plumbing or whatever you have
So
back
here, that's where they should have put one like right here.
there. And they come in a variety of sizes depending on what, like plumbers, they have big ones.
Okay, everybody knows what this is. It's a tape measure, so electricians have to measure stuff.
Yeah.
What do you have to measure?
How high you're going to put a light switch in, you have to look at how high is the light switch, how high is the receptacle.
And it's really good to have, I'm laughing because our kitchen again, the light switches were all in there, but they were all at different heights, or the outlets were at different heights. And when you get your kitchen all nice, your wife does not want to see them bouncing up along the wall. No, he didn't do it. It came that way. But yeah, you want to be consistent with your heights and
6 foot level.
for looks, for no other reason. Okay, here we go.
Quick wedge. This is slick. You have a screw?
Yeah. I don't have to-
All right.
Well, I do, but it's in the box.
Okay. Well, it looks like a regular screwdriver. But you can see the end, see how it tightens up? What this does is you put your screw on the end, you tighten this up, and it holds it. So you can go over and put it in, and put the screw in the device.
Now, for years, I would want to screw something in, and I dig through this stuff, and I find that thing, and I think, this is like useless. It's like separating and flimsy and everything, because I wasn't using it correctly. So the tool was correct. I was not using the right tool for the right job.
Linesman's pliers. They will crimp, they will cut, but they're normally what electricians use. This is what you twist your wires together. Then put on your wire nut.
And your wire nut only goes in one way.
Yeah.
You can't twist your wire this way and put your wire nut on this way. It goes on clockwise. We have these little things, they're hard to see. These are called,
Splice caps.
yeah, print connectors or splice cap. What are they used for?
You have multiple ground wires in a box. You can't just twist them together. You have to twist them together with alignment pliers, slide one of these over it, and then crimp it. Crescent wrench. You get in the panel, sometimes they have lugs that need to be tightened down like that. Nowadays, they're pretty much all Allen's. But as soon as you don't have that in your pouch, you're going to need them. Okay. Hand probe. This little device is what you would clamp over a single wire in a circuit, and then you dial it into what it's 40 amps, 0 to 40 amps. You clamp this on your wire, and it tells you that you can read how many amps it's drawing.
So remember the little cartoon where the voltage was pushing the guy through the little thing, and the Ohms guy was squeezing him and trying to keep him from going through? He was there and said he was amps. That is what tests what those amps are. How many of those little guys are going through that spot?
You get a breaker that's tripping all the time. So you would take this and put on there and watch it, see what the amperage is, why it's tripping. You could, and sometimes this would tell you that if the amperage is low and it's tripping, well, you got a bad breaker. If the amperage is real high, then you got to find out all the stuff that's on that circuit and get it changed. Normally,
Bigger breaker.
bigger.
Kidding.
Hey, I've seen it.
So, you know what the ticker is? This is his ticker. Here's a Phillips screwdriver. Y'all know what a Phillips screwdriver is?
This is one of the nice ones that has a. You can
He
clip
apparently
that.
borrowed my
Those are
straight
two-
blade
these
screwdriver,
things are
so
great.
I don't have one.
Nice to, so you're not having to go back to the truck. Electrical tape. So what this is best for is you take a napkin from the restaurant after you cut your finger and you wrap it all up.
It's not very
see-
sticky. I tried to use it to stick other things. It pretty much only sticks to
Now,
itself.
that's because this is the Harbor Freight tape. It's almost useless. If you buy the Scotch 33, it'll stick to anything.
But when you're a retired electrician, you don't. We have a razor knife.
Razor knife. Now, in the old days, an electrician would take the razor knife and run it down the middle and peel this back.
He says in the old days, but they still do it.
I was like, I still do that. What are you talking about?
Your old school people do it that way, but if you don't, he also has a very fancy electrician's knife, which is kind of like, I think it's like a Swiss Army knife for electricians, you know. I said, it's the kind of thing you get electricians like for their birthdays and stuff. It does some stuff, but it's basically just
It's
a
just
fancy knife.
stuff.
I took all that out. Okay. Needle nose pliers. That's for getting into small spaces, twisting stuff. I took everything out of the pockets.
Turn it over and start about that. Stop it.
Okay.
We gotta hurry.
This is a paddle bit, which goes in your drill, and it's for drilling, also for drilling these holes, you know, depending what you want to use. You can use an auger, or you can use a paddle bit. Just, I don't know why you
Choice,
use
whatever you like.
whatever you have.
Whichever you use.
These
the
come in different
sharpest-
sizes too.
The sharpest one is the one you'll use.
We didn't bring you one of every size because, you know.
This is the GFCI tester. This is a little fancier than the one that's not working. You can plug this one in, you can change the milliamps of what, you can see exactly what that's tripping at. Just because you have a GFI doesn't mean it trips when it's supposed to. Not very many electricians have this because they don't care. I mean, they don't. I've only used it a couple times, but it's real handy when the ground fault doesn't trip.
So here's another panel that's smaller. Allen wrenches, you all know what Allen wrenches are, also called hex wrenches. If you've done any IKEA furniture, you know what these are, because that's how you put everything together from IKEA, which we have done 75, I think, something pieces of IKEA furniture in the last 10 years. This is just another bit.
It's a fancier bit.
Running through, you know, it's called, for some reason, switch plate bit. I don't know why.
It's adjustable. You can take this center auger out. But it was a toy. When it was sharp, it really, I mean, it would just eat through the stuff. It would.
This is, you probably know, is a torpedo level, and these are mostly used for when you put your outlet covers on, because there again, if you don't use it, your wife comes in and says, "Why is our switch plates crooked? They didn't use a torpedo level." So if you want to do good quality electrical work, you always use your torpedo level to level up your plates and make sure that they're on there straight, because otherwise it looks bad. And wives care about stuff looking bad. So,
Okay.
yeah. We only have a couple
Don't
of
we
other
have to
things.
move right
A
along?
couple other things. A couple other things.
Oh, we have, oh, we do.
I have a couple other things.
She did.
I still have a couple other tools.
She's.
Channel locks. This is a little one. Just a pair of pliers that, you know, kind of has different positions, and it's for, you know, tightening up screws and stuff, or bolts, nuts, something. What is it? Tighten up?
Yeah,
Yeah,
connectors.
connectors. It comes in all different colors, all different sizes.
They do come in different colors.
And scratch off. It's basically for making starter. I won't do it in the wall.
God.
Steve's not in here, go ahead and do it.
But it's for making kind of a starter pole, because sometimes you put your drill bit up there and it slides off and puts a big gouge in the wall, and your wife doesn't like that either. So for you guys, this is for ahead someday, looking ahead, if you get married, you'll know how to make your wife happy. Use these tools.
Buy her own tools.
And this is the last one.
Nut driver. And this is insulated for 1,000 volts. Like you saw on there. I have a whole set of these. And you can put your nut on there and you can reach in and not short out against anything. That's what all of this insulation's for. Okay, part 2.
Okay, now. Oh. Here's the fun part, people. It's time for a test.
Yes, yes.
So if you need something to write with, you can use your notes, but you shouldn't need your notes if you're paying attention. You should read your notes, and
You can always use the notes on
Oh, it's just
now it should only take about 10 minutes to do this test.
All right, Peyton's got 2.
So Larry can do his own test.
I can do it, yeah.
Okay. You can start anytime. It's not like, you know, when they say you have to turn it over.
You start, you
You
can
just
talk.
circle the entire thing.
Yeah, just circle the right answer. And when you're done, we have one more thing to do before lunch, so hopefully you can answer quick. Yeah, put them down,
True.
We're in trouble now.
And you can cheat if you want that.
Make sure you put your name on your test, so
Oh, yeah.
we don't give you a perfect score to somebody else by accident.
Or bomb the test and make it someone else's name.
Could be. Might work. Well, just cut off and put them in. Cut off and put them in.
So we can announce it, so. Just extras.
I was testing it.
Just extras.
Yeah. Yeah. I want to show
No
one.
collaborating now. You done?
Sure.
Okay. I'm done too.